Off we go. Alright, so I want to talk more about animation today. We did some really cool stuff last time, so first of all, I just want to copy in to a folder for today, stuff that we did last time. So here, let me go on to my desktop real quick. Might as well make the folder while we're there, huh? And of course, I have to minimize every single thing to get to this folder. There we go. So today, I assume it's lecture 25, right? Yeah. I'm going to copy in this bounce program from last time, and I'll save it as, I don't know, bounce copy, so that you know it's the copy of the one from before. All right. So let's go to that. In idle, is there a button that I could use? Yeah, cool. That's how the world should work. Let's open up what we did last time. Here it is. And remember what happens when we run it. It's beautiful. It draws a little window, makes the turtle the ball, and the ball goes up and down and bounces. It's wonderful. All right, so this is what we had from before. I will review it in just a second. I guess the first thing I want to highlight is the fact that we had a loop, and that was like somehow that made animation, right? Because when you make like a flip book, or like you have a film with a bunch of film frames, you're showing a bunch of pictures to somebody, right? Very, very quickly. So like you show a picture of the ball up here. If you're going to make like a film of an animated ball, you'll draw one picture where the ball's up top, another picture where the ball's moved a little bit, another picture where the ball's moved some more, right? And somehow we did that in Python, but it wasn't very obvious, right? It wasn't very apparent. Like, how did we get that? So here, let's go back to our program. Here's what we got. At the very start of the program, we have this draw rectangle function, right, that drew our walls 400 by 400. It's really a square, centered at 0, 0. So that was that first bit right there. And then, right about now, we turned the turtle into the ball, made him pink, stretched him out, right? That's what these lines were doing. And then started using these three variables, turtle x, turtle y, and turtle offset, to keep track, right, of where the turtle is, first of all, where we want the turtle to be, and then also how fast he's moving and in what direction. You remember how if I made this like -5, -7, he sped up? And the negative fact meant that when we started the turtle up top, the negative is going to bring him down, because this offset is always going to be added in to the turtle's y coordinate, because that's your up and downness, right? And if you want him to move down every frame, we'll move him a little bit in the negative direction. But eventually that's going to flip when he hits the bottom, right? Every time we hit a wall, we're going to invert our offset so that we would come in one direction to hit the wall, we're going to bounce off in the other direction. So right now it's positive, now it's negative again, like at the start. Now the offset's positive 2, because we started with -2, so we want to move them up, all right? This is all coming back to us. Yeah, just shout out if you have any questions about this stuff. But there's that at least. And yeah, then we got the turtle into that correct spot. These are just variables, right? Turtle x and turtle y, they're just variables. They don't actually control the turtle. They're just for us to like plan out where the turtle should be. It's turtle.goto that actually moves the turtle who is functioning as the ball right now. Remember that, okay? So eventually you always have to like tell the turtle to actually go to those places that we planned for it to go to, wherever x and y are. And it's just y that changes for the rest of time for us. And then we had this forever loop, right? We had this, we made a draw frame function to keep track of like what to do every new frame, do stuff. But once we had that, it was very easy to use, right? It's like forever, while true is true, and it's always true. Draw new frames, like handle that. And somehow, doing this a bunch of times, we got animation, right? So that's a little not obvious why that's working. So we should talk about it, okay? So you might imagine that if we just keep doing this as fast as we can, maybe like you never get anything done at all, right? Because it would be trying to draw so quickly, it would draw everything on top of itself, right? And you never get anywhere. So like if it just kept drawing frames, why is it showing anything at all? That's not obvious. So there's that, because like maybe it would just draw frames so fast we never see anything. It's always like clearing the screen to draw the circle, but then we move the circle immediately, right? So somehow that's not happening. Interesting. All right. So the secret, the reason that loop, we never said like, I want exactly 24 frames per second. I want exactly 60 frames per second. We never said that anywhere. And yet still we're getting some kind of smooth animation. And the reason for that is because this draw frame function, really the only thing that's moving the turtle is this line down here, turtle.goto, right? That's the line that's moving the turtle and producing animation. And thanks to the way the turtle library is made, every time you call turtle.goto, like it waits for the turtle to make that movement to that place. That's what we're banking on right now. All right. So like inside of a computer, it takes a while. It takes a few split seconds, like milliseconds, to like run some lines. Like every time we're calling draw frame, we're running all these lines, right? Until we get to the goto. In addition to the goto, but like all of those lines, they take a few milliseconds, nanoseconds inside the computer, and so it's waiting for those to complete before it can call the goto, first of all, and then once it gets to the goto, the turtle library is like, I am not letting this program continue until the turtle is in this spot. Does that make sense? That's what it's doing, and that's why it's producing animation, and that's why it's waiting for us. It's just like it's baked into the turtle library, and it's kind of just doing it as fast as Python possibly can. Like as fast as Python can run these lines and call this goto function to move the turtle to the new spot that we care about, that's our frame rate. And you can probably measure that, and it's probably different on my, what is this, almost 5-year-old laptop from the school, right, versus your supercomputers in front of you. It's probably, if you run the same program, the ball might move faster for you guys. Very possible. Because Python can run these lines faster on your computers. Your processor is faster than my laptop's processor, right? But that's why we're getting animation. It's because it takes time to run all these lines, and then also the goto function. It takes time to like do the stuff, actually put the turtle, redraw the screen, get everything in the right spot, all right? So that's interesting. We're just getting animation for free. Just essentially we're asking Python to do things as fast as it possibly can, and that ends up being our frame rate, right? So you could have more fine-grained control over this. If you were going to ever make a video game engine or something, you would want more fine-grained control. Like you want to make sure your frame rate's no less than 60, no less than 30, and you'll pay the price for that. If you want, you can have control a little bit more over the frame rate in Python too, in the turtle library. There's a function in a new library, it's called the time library, that you could ask your program to go to sleep for a little bit. So it's Python time. So here's the time library, and the only thing that I care about you knowing from this one is time.sleep. So it's a little function in this library that just tells the program to stop, just pause right where you are for like however many seconds you give, and you can pass this as a float. So you go like 0.01 seconds if you really want to, and it will just stop, all right? So that will give us more control if we wanted to have more control about like how often do our frames get drawn, and then we can have it like wait until we're ready for the next one, and like slow down if it's going too fast. We can also like use the time library to keep track of like when was the last frame drawn, because I want to make sure the next one is in exactly a 24th of a second, something like that, all right? So yeah, if you want to do that, you got to import the time library, and let me show that to you. It'll make it a little bit more choppy, just for fun, but here's what we got, nice and smooth, as fast as Python can do it. And then here, let me mess with this ever so slightly. I will import the time library, and then say time.sleep in between every frame. So let's do it maybe after every, like at the very end of draw frames, like after the goto even, we'll say time.sleep, like 0.1. And so this is going to force now the program to stop for 1/10 of a second. And so we will get no better than 10 frames per second. Does that make sense? Because I'm doing that. We'll get less than 10 frames per second technically, because all these lines take time as well. But like this, it'll look choppy now. But you do have access to this kind of control if you wanted it. And you could play with that number, of course. Look at it. Can you see it? Can you see 1/10 of a second now? And so that is, I don't know, No, that's like a more old school way of doing it. And then if you wanted to, because we're slowing it down like this, we're making it more choppy, there's fewer frames per second. If you wanted it to move as fast as it did last time, you have to increase the offset to have it move more per frame, don't you? Interesting. Maybe you got to move like -10 now. I don't know. But like that's the thing. That's the thing you got to worry about. Whee! And then it looks disgusting. But that's how it works. Crazy. And we're just letting Python do it for us before. But you could have this control if you wanted it. That's just time.sleep. Tell the program to go to sleep for 1/10 of a second, or however long you want to. I think that's what I want to say. So hopefully you kind of get a feel for like why the animation was happening. Like we were drawing pictures very quickly. We just didn't really have a lot of control over how fast those pictures were being drawn, just as fast as the computer could do it. But here we are taking control if we really want to. Probably better to give it back to Python. Any questions about that? So yeah, that's animation in a nutshell. What I would like to do today, for the cool example for today, I want to improve on this program. What I would like to do is include gravity into the equation, because the ball was bouncing, right? And it was just going up and down, it would never stop. We made sure it never stops. The offset is just always +2 or -2 from the previous program, right? And it just always go up at the same speed or down at the same speed. That's not how the real world works. So let's fix it. So what happens when you drop a ball on Earth or on the moon or someplace with gravity? When you drop the ball, like at the very second you drop the ball, it's for a split second it is motionless, and then gravity takes over, right? Then it starts moving a little bit faster, a little bit faster, a little bit faster, and then it gets really, really fast. It's the fastest at the time it hits the ground, isn't it? So it's speeding up as it goes down. That's how gravity works. And then it's going to bounce. Oh, I hate PowerPoint. And then it's going to bounce. And then it's going to bounce back up slowly, 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 slowly. And then, or no, it's going to bounce up really quickly, isn't it? Bounce up really quickly and then slow down as it gets to the top of its arc. Whee! And bounce down and get faster. Slow, fast, up, slow, slow, slow. And then bounce. Boop, boop. Something like that, you know? And because they're all, if you've taken a physics class, you know that every collision with anything in the real world is not a perfectly elastic collision, and so we lose some speed every time the ball hits the ground or it flies through the air, right, with air resistance. And so eventually the ball just starts dribbling slowly and slowly and slowly, and then it stops. Our program will have that too, right? That's what I want. So in general, this is what happens with gravity, right? This is a review of physics today, I guess. So we're going to program physics is what we're going to do today. So at the very start of time, like when we start our ball dropping, it will have no speed, and then gravity will take over, and then like in the next frame it's moving very slow because gravity hasn't really taken over too much. It's not being pulled down very fast just yet, right? And then maybe the next frame it's moved twice as much because as it goes down, right, it gets faster. You drop the ball, it's like it gets faster until it hits terminal velocity, right? Faster. So maybe after one frame you move that much, but after the next frame you move that much because gravity is pulling it down faster and faster until it hits the ground, yeah? And then at the very bottom of the bounce, right before it hits the ground, it's going as fast as it possibly could have. Super fast. Because as long as it's in the air, it's being pulled down, right? So that's physics in a nutshell, isn't it? And so we're going to program physics. And the correct term for the kind of physics that we need here is kinematics, right? Hopefully a lot of us have taken a physics class. We need to talk about like speed and things associated with it. So actually it's not even speed, it's velocity, right? The ball is moving with a speed in a given direction, right? That's what velocity means. So right now our ball is moving with constant velocity, isn't it? If I go back to not our choppy program, but like last time's program. Open last time's program with the constant -2 offset. This ball is always moving the same speed. It's never slowing down, never speeding up. That is constant velocity. Okay, so that's what we got right now. We'd like to fix that. All right, that's not what happens in real life. It should speed up on its way down. All right, so velocity, right? Go back to physics again. Velocity is your change in where you are, right? Like I'm over here or I'm over here. Like velocity is your change in position. It's how fast you're changing where you are. Delta position, right? How fast you're changing your position. That's what velocity is. And velocity is going to be affected by gravity, all right? So the question is, like, in real life, how fast, because the ball is supposed to speed up on its way down. Where am I supposed to be? Here. The ball is supposed to speed up on its way down. So the age-old question is, how fast does a ball that's dropping change its speed? And the word for that, right, change in velocity, is acceleration. So what is the acceleration due to gravity? Acceleration. We have to incorporate that now. Acceleration is how fast is your speed changing? How fast is your velocity changing? Delta velocity. All right? We've seen these terms before, hopefully, right? So in real life, the ball, gravity, the acceleration due to gravity is 9.8 meters per second squared into the ground, right? Straight towards the Earth's core. So that's what happens in real life. The ball should be moving, should be affected by gravity that much. 9.8 meters per second squared into the ground. And what that means, that squared looks a little funky. It's not like easy to understand. Like meters per second, that's a speed, but meters per second squared? If you've never seen that before, what it means is just like you're dividing by seconds again. What that means is like you're speeding up by 9.8 meters per second. Every second, you're getting faster by 9.8 meters per second. Does that make sense? That's what's going on. That's how that really works. So like at the very start of time, like let's say we wanted to program this, right? We'd have a velocity variable. Starts at 0 because when you drop the ball, it's not moving yet because you didn't throw it. You're just letting go. It's not moving yet, but the acceleration is always constant, right? It's always pulling you into the ground, negative 9.8, let's say. We'll save that in a variable. So at the start of our ball bounce, its velocity is 0, the acceleration is never changing, the gravity doesn't change unless you like go onto the moon. And so what we can do is like every frame, we want to kind of because we want to program physics, we have to let the velocity be affected by the acceleration, right? It's like every second we need to speed up by 9.8 meters per second in the negative y direction. All right. So yeah, after one frame, maybe it's got to be like incorporated. We've got to bring this in. Like now the velocity should be negative 9.8 after a second, let's say. Does that make sense? And then the ball's going to start to move because now it has speed. It's negative 9.8 meters per second. And then maybe after another second, we'll incorporate the acceleration again, right? Because that's what's supposed to happen in real life. After another second, the ball should be moving at negative 19.6 meters per second, yeah? And so that's going to allow it to move even farther in the next go-around, yeah? And then just keep doing that. Boop, 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 until the end of time, until you hit the ground. Because, of course, you stop once you hit the ground, unless you go through the ground because you're going so fast, yeah? So that's what needs to happen. If we're going to program it, we have to have a velocity variable. We already have that. That's like this. That's the offset. The offset was the velocity, wasn't it? We have that already. We need an acceleration variable in addition to that and have that affect the velocity, right? And so like every time we have a new frame, we'll let the acceleration affect the velocity. And so we're going to have to like figure out what should the acceleration be, not in meters per second squared, but like in turtle land units per frame squared. Because it's every frame we're trying to update it, not every second, yeah? So we'll just make up a number until it looks good, but that's kind of what needs to happen, right? So yeah, that's how that will work. And yeah, just by doing it the way we're going to do it, it's going to eventually stop and it's going to reduce like the velocity slowly but surely. Like it'll never get back to the way it like the time it first hit the ground unless we fix it. All right. So I think I'm ready to like get started a little bit. Does the idea make sense to us, what I'm about to do? We're going to add a new variable called acceleration. That's never going to change, because like gravity is always pointing down towards the Earth at some negative value. The velocity is going to start at 0 now. It's going to be affected every frame by the acceleration. It's going to be cool. So here, this is the old program. So this is the old bounce program. I'll make a new file, and I'll paste it there and save it as bounce with gravity.py. All right, and so just as a, might as well have one more diagram before we get started. So here, let's do this. This is kind of what I want. Or I'll do that next. At the start of time, let's say maybe we'll make it easy on ourselves. We'll have a velocity variable, starts at 0. We'll have an acceleration variable. It's like some constant pointed towards the ground, so negative something. Let's just be like -1. -1 unit per frame per frame. So like at the beginning of time, the velocity is 0, so the ball's not moving. And then after 1 frame, we'll make it the velocity -1, and so that ball will move 1 unit after that frame. And then each time we're going to keep affecting the velocity by the acceleration as long as it hasn't hit the bottom yet. Then we'll make it -2, bring it in, -2, which means that frame, that next frame, the ball's going to move 2 units. Twice as much, yeah? That's what it's going to do. And then the next frame, we got to bring in the acceleration of the velocity. That's just like how the world works. Now it's -3, and so that frame, the ball's going to move 3 units. And so it's moving faster and faster and faster. The velocity is increasing as it's going down. That's what we're going to do, okay? And then we have to worry about hitting the bottom and bouncing off, but it will mostly work out, all right? It will mostly work out. So here, I'm going to change some names. So like we saw, this is just the old program. Offset is -2 right now, so it's constant velocity. Because it's the 2, right, that's incorporated into the position every time, isn't it? So that was the change in position. So this is constant right now, constant velocity, constant speed. Let's change that variable name then, because that's what that was. It was velocity, wasn't it? This wasn't, so this was turtle X and turtle Y. Sure, they can start there the same. But now it's not turtle offset anymore. It's turtle velocity. That's what I want to use. And it should start at 0, because when you drop the ball, you let go, it's not moving. So that's how it should be, all right? The initial velocity of the ball, velocity of the ball is 0. You let go and you have not touched it. It's just letting it be affected by gravity. So if you were in space and you let go, just stay there, right? Velocity is 0. And because I just changed offset to velocity, let's just mess with that everywhere. Not offset anymore, it's velocity. Velocity. Change the turtle's y coordinate by, not the offset, by the velocity. That's still doing it right? We're changing the position based on the velocity. Velocity is delta position. That's how it should be still. The velocity affects the position, but the acceleration must affect the velocity. Now that's where we're going, all right? And so every time we hit a wall, we bounce off in the opposite direction. We're about to speed off in the other direction, right? So it's the velocity, the direction of the velocity is changing. And I think that's everywhere I said offset. I can search for that. And so it's only in comments. I will replace the comments. Bam. So nothing, well, I guess I started the velocity at 0. So now if I run the program, it's still going to work, but the ball's not going to move anywhere. We're in space. So now let's find some gravity, all right? Let's find some gravity. So let's do this. So we want, in addition to turtle velocity, we want turtle acceleration, all right? Equals something that's some negative number. We'll figure out a good one. I don't know. We can start at -1 maybe. -1's probably fine. But the units for acceleration, because just like for velocity, it's not like meters per second. It was like units per frame, because we're moving that much every frame. So just in the same vein, like the acceleration units for this acceleration variable are units per frame squared, pretty much. Because like every frame, this is in draw frame that we're going to have it be affected. Every frame, we're going to change the velocity by a certain more units per frame. Because that's what the velocities units are, units per frame. Cool. That's how much it's moving every frame. I think that's what I wanted to say. Does that make sense so far? So that's our new variable. It's going to be towards the bottom, so negative direction. But that's pretty much it. And now I just want to play this game, like I was saying here with this variable or this variable. Every round, the velocity is going to change. I want the acceleration to affect the velocity every frame. All right. And so there's only one place I have to do. It's just kind of right here, right? Just like change it, the turtle's y coordinate by the velocity, and then also change the velocity by the acceleration. I guess let's do it first. Let's have gravity take over first. You can do it in either order. It would just be, it would take another frame for it to like get into the new velocity if you did it in the opposite way. But let's have the acceleration affect the velocity first, and then the velocity can affect the position. I think that's a good order. So the acceleration affects the velocity. And so what does that mean? I want every round, the velocity, I want to just add in the current acceleration, which is never changing because we're on the same planet always. Add in the velocity, add in the acceleration into the velocity. Have it affect it, all right? So that just means turtle velocity is going to change. Turtle velocity equals whatever it was plus the accelerations being affected by the acceleration. Does that line make sense to us? That's what we needed there. So that is going to change how fast we're going each round, which means this is going to get smaller and smaller and smaller as we're going down. And so that means it's going to speed up. It's going to move more frames every second because the velocity is going to affect it more because there's more speed. Because the acceleration is affecting the velocity, making it smaller, I guess. And so that's pretty much it. I changed some variables names. I added this variable, acceleration. I had the acceleration affect the velocity. Everything else is the exact same with just slightly different variable names. And that will make all the difference. Watch. Whee! You see it speeding up? Well, look at it go. And a fun quirk of the way we've programmed it is just losing speed every time. And so it's about to just bounce and stop. Was that not so satisfying? That was one extra line, more or less, wasn't it? Maybe two if you count the definition of the acceleration variable. We just programmed physics, and it only took 2 extra lines. It's so beautiful. I love it. So are there any questions about what we did? Like, do we understand like the things at play here? Just the new variable, have the velocity be affected by the acceleration each round. It's going to pull it down faster. You see it speeding up as it gets towards the bottom. I still need to talk about like why it's stopping because that's not obvious right now. But that's how it works. If you want to be on, like, let's pretend we're on Jupiter, we can increase the acceleration because that's increasing the force of gravity. So it's double the force now. It's going to be sped up faster. Ooh. That's not a huge increase, is it? Let's make it like -5 or something. But yeah, it's being pulled down faster. You see it there. Well, let's make it huge. It might look choppy if we make it too big, but that's okay. This is fun for us. And it stops so soon. I don't know, let's try 25 to see the effect. Whee! Ooh. There we go. So yeah, that's very heavy. It's on the surface of the sun or something. That's what would have happened. Alternatively, if you want to turn gravity around, you can make acceleration positive, couldn't you? 5 or 1, whatever it was. Now it'll bounce up, won't it? Which means it's not going to go anywhere because it's already up there at the top. So we need to like start the y somewhere else. I don't know, for a split second we can start at like 0. Then it will be pulled that way. Pulled up. Whee! So gravity has been inverted. So like that's how you program that in a video game or something. Just change the acceleration. Cool. Let's go back to how we were. I hope that makes enough sense. -1. If you want, or let's make it fall even slower. Maybe like -0.5. Now we're on the moon. Yeah, it bounced up even higher. So, all right. I think now I need to talk about why is it actually stopping? Because it's like it's losing energy every time it bounces, and we didn't program that, did we? That's not anywhere. That's just a quirk of what we've done. So technically we did program it, but we didn't actually explicitly say something. But it's cute that it does that. I like that very much. So that's just a quirk of what we've done. The reason it's eventually stopping, because we didn't program it, you'd think that like when you multiply it by -1, it would just like shoot off back up to where it started again. Because we didn't have it lose any energy. We didn't subtract any velocity. But technically we kind of did. So here's kind of what happened. Here's why it eventually stops due to our current way we programmed it. We made an inelastic collision. We got it for free. So like what would happen if it didn't lose energy is it would shoot back up as fast as it came down. Yeah. But it's not doing that right now. And one of the reasons it's not doing that is because really when we hit the bottom, we're not actually ever hitting the true bottom. Sometimes we're trying to go past the bottom, aren't we? That's one reason for this, because then we shoot it back up, and like we give it like slightly less speed because of that. It's being shot back up from, like we're moving it over, and like then also changing the direction, so like it's as if it had been shot up from down here, but we've moved it here anyway, so like it's lost speed in a way. And then it's just also because of the way we're doing things here, like that order also has something to do with it. So I can print for you like what's happening. Let's print the speed of the turtle every time a frame happens. So every time we do something, let's print the current turtle velocity. And then you'll watch it, like it's never going to get back as high as it was before. It's going to appear here, the speed. There it goes. Whee. So that was a bounce. And so at the very start of time, look, the speed was, well, it started off being affected by gravity. And so the initial speed was actually -0.5. It's also the order of this. That's taking over. So eventually down, 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 down. When we bounced, we shot off. But also that same round, we were affected by velocity. So we didn't shoot off at -19, we shot off at 18.5. Does that make sense? So we're just a quirk of the way we've programmed it, we've lost some energy. If you want, whenever you hit the bottom, you can remember this special number and shoot back off at that exact number. That would work. So that's kind of what's happening right now. So I'm going to comment out this line, so it's not going to be printing anymore. But it's only ever the bottom wall right now that we're ever going to hit, isn't it? But if you want to shoot back off at the same speed, you can just like, instead of this, be like, turtle velocity, make it exactly +19, right? Shoot back off at the same speed if you hit that wall. And this is like this number you have to figure out based on your initial acceleration, because if this acceleration was different, it would have been a different number, wouldn't it have been? So you don't have to worry about that. So that's like, you can just hard code that if you want to, and that will create a perfectly elastic collision. So it's like, it didn't lose any energy due to friction or air resistance or whatever. Create a perfectly, that's the physical term, right? Perfectly elastic collision by hard coding the new velocity. And that's just the way we did it. That's kind of the way you got to do it. Unless every time you hit a wall, you like want to undo this change, that would also work. Up to you. And so now, when we run it, every time we hit the bottom wall, we're shooting back up with 19 speed. And now it's always going to bounce back up to the same place. Not quite. Yeah, exactly. This is perfectly accurate to physics, more or less now. Beautiful. Could be a bouncing basketball for sure. Just to prove this to you, let's we can turn this print back on. Why not? And we'll see it bounce. So this number is going to get small velocity in the negative direction. Boop. Bouncing positive. And so every time it bounces, just we coded it this way. We shot off at positive 19 technically, but the next round it was affected again. But it was never losing any speed because of the way we did it. So it's always going to shoot back up, even though it might lose some energy. We shot it back up. It's really going to be 18.5 once it gets affected by the thing, but that's fine. That's fine for us. But yeah, that hard coding will fix it. Any questions about this? I think that's as much as I wanted to say. It's just a really cool thing you get for some variable changes and like 1-2 lines extra. Suddenly you have physics, you have gravity. I think that's really cool. All right, so if we are happy with that, I'll give you this code, of course, to play around with. You can turn back on the friction if you want by changing this back to just like negate the thing. That's fine. But it's beautiful, a little bouncing ball for us. Yeah, so please study this. This is a fun little program. It's a little complicated. The next thing I want to talk about, we're not going to program this today. We're going to do that next programming lecture. But I want to like recreate this. Remember this Office episode with the little bouncing DVD screen? So I want to do the following. Right now we've got a ball. Right here, let me just show this to you. I need to stop the recording though, because otherwise it will give me a copyright strike on my YouTube. Boop. So like right now we're bouncing straight up and down with our ball. It's going down and it's going straight back up, one axis. What I'd like to do is this. I would like to have a second axis. We'll turn it into a square instead of a ball, why not? And then we're going to like bounce off diagonally and then bounce off the wall diagonally, like go that way, and then bounce off that wall diagonally, and just like keep going, boop, 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 and eventually maybe we'll hit the corner. Who knows, if you wait long enough. That's what I want to do now, all right? It's going to be a lot of the same stuff, but now we have another axis to worry about. That's going to be the new stuff, all right? So we're just going to plan it out today on paper, and we will code it up in the next programming lecture, all right? So we got to figure out how to do this. How in the world can I take the program that I've made so far and change it to move sideways? So that's going to be what we're going to do. All right. So let's plan it out. So the very first thing we need to do is still draw the little square. We got that already. Check. At least we can reuse that. So keep all that. Boop. So do that still. And then we need to make a square somewhere. It doesn't have to be at the very top anymore, right? Like the circle was. We can put the square anywhere, make it go to a random location within the boundaries of our screen where it's fitting. So like make it go here or something, that's fine. And then its coordinates will always be relative to its center, just like for the ball, so we gotta worry about that. But that's a job for later. And then we need to, like, let's make it different every time, right? Because we're not a ball starting up here and only going down, we could go anywhere, right? We could start out going that way, we start going that way, any direction. We should be able to pick any random direction, any 0 to 360 degrees, right? Anything in between. So we need some way of picking a random direction now. Okay, we'll think about that. So let's say that we've somehow figured out how to represent that direction, and we've chosen, like, that's my direction to shoot off in. All right? Then what? Once we've got it, what do? We'll figure it out together. So we need to somehow move in that direction, understand that we need to go that way a little bit, move in that direction if we can, if nothing's in our way. Like, yeah, there's room for me, I'll go there. You want to keep doing that forever, as long as you can, right? Keep moving in that direction until you can't anymore, right? So there's going to be collisions checking, just like we were doing for the ball, hitting the wall. It's like, in addition to the top and the bottom wall being hit, we now have to check for the side walls to be hit, don't we? We don't have to worry about that. But yeah, just like do that, same as the ball, except maybe left and right wall in addition to the top and bottom wall. And then every time we hit a wall, we notice that it's not just like we were going up and we're going down now. It's we were going up and right, and now we're going down and, or sorry, we're going up and right, now we're going down and right. So like our direction arrow, it was this. It needs to become, is that accurate? That, right? So we need a way of representing directions in a way that we can change it easily if we bounce. See that? So we need that. And then we just like, we keep playing that game, right? Now we're not hitting a wall anymore. Let's move in our current direction. Our direction has changed. So go a little bit over there, and then a little bit over there. Same direction until we hit a wall again. And then we were going, this is now the right wall. We need to check for, did we hit the right wall or the left wall? So we were going down and right. We need to go down and left now. See it? Interesting. So our new direction is this way. It's like, it's a loop though, once we have this ability, right, of representing all these things, just like, that's our loop. It's like, move in your current direction if you can. If you cannot, you've hit a wall. Deal with it by changing your direction in the appropriate way that makes sense. All right, so we've got two axes now. Top, bottom wall. In addition to like top and bottom wall, we also have left and right wall. All right, we have so many options, and we just have to incorporate that. Do those ideas make sense? I haven't told you how to implement them. Do we see what we need now? We need to represent all of that inside of a program somehow. It's going to get cool. We're going to get very interesting. All right, so we have to zoom in now. Like, what in the world do we need here to make all this work? So this is why you have to plan it before we do it. So, okay. We need our bounding square. We can program that. We already have that at least. Bam, that part's done. Just copy and paste what we had from before. And then we need a turtle at a random spot. That's not too hard either, right? Because the turtle can become the square. You can turn the turtle into a square rather than a circle. That's easy, all right? That's fine. And then you could tell him to go to a random location between, like, this is what? -200 to +200 and the x and the y. Just, like, put him somewhere. Pick some random numbers for x's and y's. That's fine. We can do that. That's not the hard part. And then we will have placed the turtle somewhere once we've done that. And the turtle's coordinates are relative to his center, so we do need to be careful about like not choosing exactly -200 because that will put him like right there. We do have to be careful about his size and all that, but we'll deal with that later. But once we've got him in a spot, we need to pick a direction as well, right? A direction that we want to move in, okay? And so like we've got our turtle, like maybe we choose this random direction, but we could have chosen any direction. Like anywhere we want to go, the turtle should be capable of going. We could go this way, it could go this way, it could go this way, and anything in between too. An infinite number of arrows I could be drawing right now. We could pick any of those random directions. Now the question is, how do we represent that inside of a computer? All right. So if you remember what we were doing for the ball was we were representing the direction, like sorry, it's not really just direction, it's speed in a direction, isn't it? Because it's like we made the ball's speed, what? It was -2 speed. It was -2, which moved a little bit. If you make it -5, it's going to move even more, right? So it's speed and direction, because negative meant negative y direction. That's what we were doing already. And every round we were having the ball's position be affected by its velocity. So like it started out here, it's -2 now. With the constant velocity, it's -2 now. It's -2 now. We kept moving it down by that. And so technically this was a down arrow. This variable represented a down arrow. If it was negative at least. If it was positive, it represented an up arrow. It's like, do something to the y. Does that make sense? That's what that variable was doing for us. And so technically, that's one axis direction. We just need 2 axis direction now. It's like if we want the turtle to move, not just down, but like down and to the right or down and to the left, there's got to be a way, right? So if you think about it, we were using a single number for our up and down direction, because we have an addition of a left, up and down, and a left and right direction, we can just add another variable, if you think about it. That's not too bad. We can use a second offset. Watch. So let's say I want the turtle to move in this exact direction, so up and to the right. I can represent that by every round, Mr. Turtle, I want you to like start here and go here next. Like it's always relative to a center. Do you see how I can keep track of that direction? Like in the next frame, I want you to go from here to here by saving two numbers, by saving how far you need to go that way and how far you need to go that way. See it? Save it as a right triangle. So it's like maybe, I don't know, it's like you need to go right 3 units and then you need to go up 1 unit. So increase the x in the positive direction by 3, increase the y in the positive direction by 1. Do you see if you save both of those numbers, the 3 and the 1, you've saved that direction. Hoo-hoo. So like that's, in addition to like what we had was like a delta y, go negative 2 units. That was what we were saving with our velocity from before. But now we need a delta x. So like our delta x is 3 units, our delta y is 1 unit. That will represent a 2-dimensional direction. See it? So because like now, like if we started here, like if this was like 1, 1, we will just now move, we'll know to move to like 1 plus 3, which is 4, 1 plus 1, which is now 2. So now you went from 1, 1 to 4, 2, and that was the right direction. You can represent a direction by 2 numbers, an x offset and a y offset. How far do you move left and right, and how far do you move up and down, all at once. All right? Are there any questions about that? Please yell at me. Because like next round, what do? You want to move in the same direction with the same speed, so you're going to have it be affected, the location be affected again by the 3 and the 1. So 4 plus 3 is now 7. 2 plus 1 is 3. It's like that's where it should be now. See it? So yeah, in general, you've picked a direction and need more room. Oh, you cannot do it that way. Okay. In general, you have picked a direction. Like if you've chosen this direction, boop, just like that. You want to go from there to there. That's how you want to move. You can always think about that in terms of, all right, to get from there to there, I need to go a little bit in the x direction. I need to be nudged left or right. And then I need to go a little bit in the y direction. I need to be nudged up or down. So it's a right triangle. It's like how far are you moving in the x direction and how far are you moving in the y direction. So just a second variable is all we really need. And so if you want to pick a random direction, pick some random numbers for the change in x and for the change in y. Do you see it? Are there any questions about that? It's going to be so cool. So that's what we're going to program next time. We have to talk about it today, just to be ready. So remember all this for next time, next programming lecture. There's one last thing we want to worry about. Because if you were to pick random numbers, you may stumble upon the same direction, but a different speed, and that might be weird. So if you think about it, this direction, there's a million ways to make that direction as one of these delta x's, delta y's, right? Because you could have chosen like, I don't know, let's pick some numbers. Let's say this is like perfectly 45 degrees, so it's like 1, 1. Move 1 that way and 1 that way, yeah? You could have also picked that direction, couldn't you have? And that's the same direction, but it would be a different speed, huh? This is like 2, 2. Does that make sense? Maybe we don't want that. And I think we wouldn't want that, because like every time you rerun your program, we want to pick a random direction, not a random speed, right? So somehow if we stumble upon either of these, we want like a way of making sure that like divide by it, so that we make sure that the length of our arrow is always like 1. Yeah? Because that would give us a constant speed no matter which random direction we've chosen. If we randomly pick to go that way, either, doesn't matter which numbers that we chose to get that way, we'll like always shove the arrow down to be of length 1. That's kind of what I want here. Does that make sense? So we'll have to worry about that. That'll be a job for next time. Okay? So we'll have to normalize our direction vector, or the words that are involved here. But that's complicated. So yeah, all I just want you to get out of this slide is that we can store a 2-dimensional direction by, in addition to a y offset, which is what we had from before, add an x offset. Add a nudge in the left or right direction in addition to a nudge in the up or down direction. Okay? I think that's what what I wanted to say for that. Because like the last piece of the puzzle now is like, all right, every round we change our position in our x and y location of our turtle by that delta x, by that delta y of our direction, as long as we can, right? As long as we can. The last piece of the puzzle is like bouncing. If we hit a wall bounce, how do we take this direction and change it to that direction? We hit the top wall. And vice versa for all the other walls. That's the last piece of this puzzle, right? We're ready for that? Let's figure that out together. So here, all right. We know when we hit walls. We have that code already. We understand what happens when we hit a wall. This is what's true when you hit the bottom wall. This is what's true when you hit the top wall. You can very easily extrapolate that if you hit the left wall, it means that your x is really small, right? Relative to negative 200 plus the width. That's exactly what you'll check for. Just to make it easy on us, let's pretend it's exactly negative 200 for a slide. It's really negative 200 like plus the width over 2. But like here's our bounding square again. This is where the magic happens. That's where we're drawing our animation. And we made sure that that is a 200 by 200 box, right? Those lines aren't straight enough for me. At least PowerPoint can do this now. If I leave my pen here long enough, it'll make a perfectly straight line for me. Sometimes I don't want it to do that, but this is a perfect time for that. Good job, PowerPoint. All right, so this is what we have. And then we made, like that's 0, 0. This is a 200 by 200 square where we're drawing our animation. And so we know then, if it's, it's 400 by 400, excuse me. 400 by 400. So we know that this then is, this is y equals positive 200. This is y equals negative 200 land right there. Why are those dashes going off? I don't know. There's y equals negative 200. And just the same, this is x equals negative 200. This is x equals positive 200, yeah? And so now, we know when we hit walls. Like, all right, we hit the top wall if it's the y that was too big. The y was like 200. We hit the bottom wall if the y was negative 200, yeah? Or if we tried to go outside of it. So it's like a less than kind of thing or a greater than kind of thing. You also have to consider the width over 2 because it's like relative to a center. But let's just pretend we don't care about that right now. Same for the x, right? And for the left and right, well, it's going to be relative to the x. Like we know if we were moving, boop, and somehow we got to like right here, we were just grazing, right? We're just grazing that left wall. If something is true about our x coordinate, right? We know we're right there. If it's our x coordinate, it got a little smaller. The x coordinate is like negative 200, yeah? Plus the width over 2, we'll deal with that later. That's how we know if we hit the left wall, right? It's like that. Or if we try to go outside to less than or equal to. And then same for the right wall. We've hit the right wall if the x coordinate is big. It's like positive 200. Or we try to go outside. So greater than or equal to that, positive 200, right? So same exact stuff, just with x's, right? So same stuff that we had. That's how we notice if we hit a left wall or a right wall. And now the question is like, all right, we know how to check if we hit a wall. Bless you. What happens if, like, well, maybe we hit a corner, we'll have to deal with that. Like, what if we hit a top and a bottom wall, top and a left wall all at the same time? But, like, what if we hit a wall? How does that change our direction? All right, so we know how to check. We just need to figure out how to have that wall collision affect our direction. All right, so let's figure this out. So let's say we did hit this left wall. What do we need to do? Let's draw a picture and try to figure it out. I guess, I'll keep that where it is. So let me zoom into the left wall. Here's the left wall. We came in like this, right? Think about what we had that got us here. We had a direction like that, didn't we? Which was made up of, we're saving this direction as a delta x and a delta y. Like the delta x, the change in x was like negative something. The delta y to mean up what must have been positive something. If we're coming in this way when you hit the wall, we want to bounce off. Let me draw this accurately. We want to bounce off that way exactly, right? That exact direction. do you kind of see how you could get that? Because like the direction is a right triangle. Do you see how you could get this triangle, the like the x's and the y's that make up it, from the one that we had before? Do you see how it's almost the one that we had before? Do you see how the height is exactly the same? The y, the delta y is not changing. We're still going off up at the same amount up. Yeah, that didn't change. So that's something to notice. If we hit a left or a right wall, it's delta y is staying exactly the same. It's delta x though. We were coming left and up, right? We were coming left and up. We hit the wall. We need to shoot out right and up. Does that make sense? And it's right by the same amount, like this same width right there. You see it? That's the secret. It's whatever this delta x was, but in the other direction, negative it. That's what happens when you hit a left wall or a right wall. Does that make sense? Exactly same thing is true for the right wall. Draw the picture, I promise. Right? So that's the game. If you hit a sidewall, negate the x offset. I think you can imagine you're going to negate the y offset if you hit the top or the bottom wall. So let's draw a picture of the top wall. Let's see that working. So let's say we have hit the top wall. Boop. We were coming in like this. We want to bounce off like that. Let's draw a picture of what must have happened. So initially our direction was this. It consisted of some like delta x and delta y. It was like move positive x, right? Nudge to the right, and then also nudge up, so positive y. And then we want to move, we're going right and up, right? Now we want to move right and down. Yes? It's the y that's changing. So now we wanted that direction to change into this direction. And so it's the same triangle. You see it's got the same length for the x. Still go right by the same amount. Delta x is the same. But the delta y, it's still the same size triangle, of course. It's just we're going down, right? Negative delta y. I've run out of space. Whee! Just like that. Negative delta y. Does that make sense? That's what we need. And same for the bottom wall. Draw a picture. It's going to be the y is going to flip, but it's going to go from negative down to up, kind of. That's what it'll look like. All right. So that's what we need to program. It's like if any of these things are true, we'll have some more if statements for the left and right walls. We want to flip the sign of one of our direction coordinates, one of our direction numbers. So it's like we're going to flip the x offset. If we had left or right wall, we're going to flip the y offset if we had a top or a bottom wall, leaving the other ones intact. If we hit a corner, this is why we'll keep it like as ifs rather than elifs, because we want like both of those to fire. Like notice that we hit the left wall, and then also notice that we hit the top wall. We'll do both. If you ever hit a corner, perfectly. That's what we want. All right, so just to zoom in and get the nitty-gritty details, I'll have one more slide of drawings. And we'll be very prepared for next time. All right, we'll go straight to code. So, okay, let's draw a picture of hitting the left wall. Again, let's zoom in. Here's the left wall. And here we are. We came from here. And let's say that we have exactly this direction. We have go over 2 and up 3. 2, 3. So it's really negative 2, 3. Right? X is getting smaller. That's our direction, let's say. And so let's say that we are exactly at this coordinate, or exactly at negative 198, 2 or something. And so we're going to be, every round, we're being affected by our direction. So we were there. The next frame, we're going to move over 2 to the left and up 3 and hit right there. This is not completely accurate because I have to deal with like the width over 2, but let's pretend we don't care about that right now. Whee. So then we're going to be affected by that. So negative 198, that's our x, minus another 2, that's negative 200. And then we were at 2, we're going up 3. So now we're at negative 205. And we hit the left wall. Our if statement fires, we notice that we've hit the left wall. So we need to bounce off the left wall. And what that means is it's a sidewall. So we're going to negate our x offset. We were going left and up. We now need to go right and up. by the same amounts though. So our direction is going to go from there to, it's going to do that in a second, right? So it's going to look like this. It's going to go right 2, so positive 2 on the x, and still go up 3, still positive 3 on the y, right? So that's what needs to change. And so to get from here to here, what we did, right, our old direction was we went left 2, negative 2, up 3, positive 3. And now on the next round, we flipped our direction. So after that frame, we're going to be affected by our new direction. And that's going to be this one, right? I'm doing my best to draw this to scale. Something like that. That's our new center point. So we will have gone then from here to here because it's going to be 2, 3, right? So it's plus 2 in the x, plus 3 in the y to put us at negative 198 again. And now it's 5 plus 3 is 8. All right? So that's kind of the details of like inside of our loop. All right, we haven't hit the wall yet. Keep being affected by our current direction. So move over 2 in the x, move up 3 in the y, get us to there. And then we have hit a wall. Notice that change our direction. So our x offset's positive 2 now. Like we negated the x offset from negative 2 to positive 2. The y offset stayed exactly the same. And now next round, next frame, we want to move from here, be affected by our new direction, which is again going to involve like, all right, move over by our x offset, so add 2, and then move over by our y offset, so add 3. Okay? You kind of see how you might implement that. It's going to take some thought. Like, I mean, the devil is in the details, but we have ironed out most of the details on paper at least. So a great exercise for you would be to take what I just wrote, try it yourself before next time, see if you get the same thing that I'll get, but you're just going to need a second variable, an x offset in addition to the y offset that we had from before, because that was moving us up and down. All right? This is a y velocity kind of thing. Okay? Any questions about any of that? That's going to be our job for next time. All right? So, yeah, the last thing that I want to do today, plenty of extra time, is release your, I think this is your second to last programming assignment. So not exactly your last programming assignment, just like this was your last essay, but this is your second to last programming assignment. You'll have one more. This is your goal. This is why we had to do animation twice this week. I would like you to make this program that's very similar to what I did today, but I want you to add some stuff. So what I want you to do is take my, like, not the program from this time, we just like had to review it. Take the program from last lecture, this bounce program, the one with just like the offset name, wasn't velocity yet. Take this program. So go into the code from class, steal all of this. So use my code as a starting point. And then remember that this program bounces up and down. So it's always going to hit the top wall. It's always going to hit the bottom wall. It's never going to miss any of them. And so what I want you to do is program the top and bottom walls to be magic. All right? So every time in your programming assignment, every time you hit a top wall or a bottom wall, oops, I closed out of it accidentally. So take my code from before, draw that bounding square, make an animated ball, bounce up and down, steal all that. I already gave that to you. And then here's what I want to have happen. Every time your ball hits a wall, I want you to hook into that code. It's those if statements, right? Hook into the ball hitting the wall and make something weird happen. Make it magical, all right? So here are some weird things that you could program. You could choose to program. You could change the color of the ball when it hit the wall. You could change the size of the ball when it hits the wall. That's this bit right here. The size is this stretch thing, turtle size. You can mess with that. The color is the fill color. You can mess with that. You could change the x coordinate of the ball, just like warp it over. That would work. That would teleport it. You can change the speed of the ball by some factor, either slower or faster. That would be the turtle offset. We multiply that by something like 0.5, by 2, of course, by some random value between 0.5 and 2, something like that. So that would work. You could randomly change the shape of the turtle to something other than a circle, because here the turtle library has a bunch of options for you. You could change it from a circle to, like, there's a square. There's a square, there's a triangle, there's the turtle that we know and love. So I can change its shape randomly, just like I was doing there. And I want you to just like randomly pick one of those ideas, all right? So here, that's essentially your goal. If you want a random number, like with decimals, instead of random.random, you have to use random.uniform. That will give you a random float rather than a random int. You might need that. But like, here are some potential options. And what I want you to do is make a new function. So this is really me forcing you to remember how to do functions. So make a new function, please, called like do something weird, or like bounce off magically, or whatever you want. Make it be called something cool. Make a function, and I want you to call that function to choose some weird thing to happen. So like, don't always make the color of the ball something different. Like sometimes make the color different, sometimes make the size different. All right. So I want you in your function to randomly pick some weird magical thing to do. All right. Every time you hit the ball, every time your ball hits the wall, call your magical function. That's what I want, and then have it pick some random thing to do. You can choose one of these or make something else up yourself, but you better program at least 3 different magical weird things to have happen that you choose from each time. You're going to flip a 3-sided coin to figure out like which of those things should I do right now. All right, so that's the setup. Here is here's kind of a picture. A picture's worth 1,000 words. That's kind of what I want. Like when your ball hits a wall, change the x direction, the speed, the color, the speed, the x direction, the size, the speed. All those are options, right? So randomly, every time you hit a wall, pick something to do, one of your random things that you've pre-programmed to do, and have it happen. Does that make sense? I want at least 3 random things, 3 possible things of happening, so that it's not always just like, I will change the color, I will always change the shape. Be a little bit different. Like this time it was the shape. This time it was the speed. This time it was the color. So I have those 3 maybe. That would work. Does that make sense? That's what I want. And I want you to get practice with functions doing it. So like I want to make sure this happens in a do something weird function. And you'll call that whenever you hit a wall, which is just these if statements, right? That's when you hit the wall. Yeah. So yeah, as a hint, I got this. You can read this. Here's how you can pick a random thing to do. So say that you've pre-programmed 5 different things. I know that, all right, I know how to change a color, change the shape, something like that. You got 5 weird things ready to choose from. Here's how you, like, each round, you hit a wall now, which one do I do? Here's how you can pick that. You can use a random number. So, like, pick a random number with a random.randint and put that into some variable. And then you can use a big, long if-elif to be like, if the random number was 1, okay, I'm going to change the color. If the random number was 2, okay, I'm going to change the shape. If the random number was 3, I'm going to change the size. Does that make sense? That's how you could pick the random one to choose from. So like each round, find a different thing to do randomly. Okay? I think that's what I wanted to say. So you can use that as like a starting point. That's kind of what it should look like if you programmed a million things. But you only need 3. So forcing you to use functions and random stuff and building on top of this complicated code. All right? Are there any questions about any of that? So you got a few weeks to do it. Please ask me questions if you're having any trouble, and I will be happy to help. But I think that is all that I wanted to say for the day. So if you want to ask questions about stuff, there's plenty of time right now.